Hi guys, in my previous concept I discussed about Ampere Circuital law. This law is very handy, very easy than the Biot-Savart's law to apply to find the magnetic field at a given point to a current carrying conductor. So this law states that the line integral of magnetic field around a closed circuit equal to mu naught times the total current I threading or passing through the closed circuit. In mathematical form, closed integral B bar dot dl equal to mu naught I. So here closed integral B bar dot dl bar equal to mu naught times I, here current I enclosed. So to apply Ampere Circuital's law, so we need to imagine an Amperian loop. So something just we need to carry always, just like this honeybee net, depends upon the structure or depends upon the conducting material, current carrying conducting material what they give. So we tried certain examples. Let us try to find in a real case, try to find the magnetic field to this given condition. So the problem says the following figure shows a long straight circular cross section of radius little a carrying a steady current capital I naught. So here take that it is I naught. The current I naught is uniformly distributed across this cross section. Calculate the magnetic field in the region when R is the magnetic field we need to find at a point which is greater than the radius and R is less than the radius. So the following figure shows a long straight wire. So through the wire a uniform current I naught is passing. So our task is to find the magnetic field at a given point. Suppose I would like to find the magnetic field at a point which is far away from the radius, which is outside. So let me take it here. I would like to find the magnetic field at a point P which is at a distance R from the center of the straight conducting wire. So to apply Ampere's law we need the following things. So the first step we need to get that appropriate or proper Amperian loop. Proper Amperian loop selection. So here I would like to take a circular Amperian loop. Since it's uniform, so we need to get that formula easily. It is easy to apply. So this Amperian loop which is fixed to the current carrying conductor. So just like it's a ring which is fixing to my pen. Now the Amperian loop radius equal to R. Now if I write the formula, so closed integral B bar dot dl bar equal to mu naught I. So this is the formula. Now second, the step what we need to bother. So second step we need to bother what is the current enclosed. Current enclosed. So the Amperian loop is enclosing the total radius of the conducting wire. So since it is enclosing total radius of the conducting wire, I naught is the total current which is passing through the conducting wire. So in this case current enclosed equal to I naught itself. Now the third point, so from here I got it about current. And mu naught is a constant, we need not to bother. And finally we need to bother about closed integral of B dl bar. So what is the dl bar at here? dl bar is an elemental length in the Amperian loop. So if I take a small element length in the Amperian loop, not in the current carrying conductor. Very important point. So this small elemental length we need to consider in the Amperian loop. So here nothing to do with the current carrying element. So this is the small elemental length which I consider. So this is the small elemental length dl. Now if I do the integration to the total of that, now this total is just like a circle of circumference 2 pi r. So which I am going to highlight. So this is the total integration I need to do to my Amperian loop. Now in this case, the third point what we need to get, the closed integral of dl bar. So in this case that equal to 2 pi r. Here r is the radius of the loop. So like this you section separately, then easy to apply. Now straight away let us apply in the given formula. So the magnetic field at a point. So magnetic field at a point B suffix P. So this is which is greater than the radius of the point which is greater than the radius of the conducting material. So closed integral B bar dot dl bar equal to mu naught times current enclosed. So substitute the values. So here we have all the values at here. So B bar which we need to find. So I will take out of the integration. Closed integral of dl bar equal to mu naught is constant. Here current enclosed the value equal to I naught. And B bar times closed integral dl bar. So that is a circle of circumference 2 pi r. So we got it that B bar times 2 pi r. Which equal to mu naught times I naught. Yeah, now we got the magnitude of magnetic field B bar. So it's just magnitude. So better I will leave that vector notation since it's only magnitude. So B bar equal to mu naught I naught upon 2 pi r. So it's only the magnitude. So to get the direction, we will apply the right hand rule. So that is another task. So right now I am only concentrating about that magnitude of the magnetic field. Now this is the magnitude of the magnetic field at here. Suppose what happens if I wish to find instead of at P, now I wish to find at a point at Q which is far away. Now this time I am drawing at here. Now I would like to find the magnetic field at a point Q. So this is also which is far away. Now this distance if I take that as r suffix 1. Now how can I proceed? So we need to consider same type of Amperian loop, but this time the Amperian loop will be much bigger. So the Amperian loop in this case should be bigger. Now this is the Amperian loop which we need to consider. If you look at this from the top view, so these are just like the Saturn rings or concentric circles, so which I am going to highlight. So this will be includes everything. So I need to highlight from everything the yellow region also. So this much is the very big Amperian loop. How far we take? So that much is the magnetic field is uniform around in this Amperian loop. And throughout the Ampere loop, the magnetic field is always tangential direction. So this is one more important point whenever you are up preparing for the competitive examinations. So these small things are very weighted. So where others do not concentrate, there you should concentrate. So this is the direction of the magnetic field around the tangent. So this is the B bar, tangent direction, to the always to the Ampere loop. Now to this case, how this formula going to change? Nothing to find. Just you can replace the closed integral of B bar. So this is at location Q. So if I write this at Q, now in this formula what is going to change at most? Mu naught, it do not change, and I naught, it is also do not change because current is enclosing towards stem, and 2 pi times. Now here instead of R, I consider that it's R1. So 2 pi times R1. Now from these two formulas, so the magnetic field at a point which is out of the radius and which is far away from the radius, which is R1. So from these two formula we conclude that. So in this formula, mu naught, I naught, 2 pi all are constants. They won't change because I naught is also uniform current is passing. So the magnitude of magnetic field is purely dependent in this case. B is inversely proportional to R. It means when you go far away from the current carrying conductor, the strength of the magnetic field, what happens? It decreases. How much it is decreased? It is decreased with 1 over R. So in this case, the magnitude of the magnetic field is decreasing with 1 over R. If you go far away up to infinity, so obviously it goes to vanish. So this is one more important point. Please try to remember. So for a current carrying conducting wires, or for a current carrying conducting wire, the strength of the magnetic field is inversely proportional to the position where we are measuring. Now these two cases gives to me when the R is very greater than the A. Here A is the radius of the loop. Now the second case is given that when R is less than A, it means the point of magnetic field we need to find which is less than the radius of the loop. Suppose this is the cross section view from the top angle. From the current carrying conducting wire, we are looking from the top angle. Now here you can see, we consider a Ampere loop inside the current carrying conducting wire. Here the current carrying conducting wire, Ampere loop is considered inside, since we need to find the magnitude of the magnetic field inside it. Now what is the amount of current is passing through the conducting wire? That equal to I naught. So if I draw the same figure, you have saw that the current carrying conducting wire is carrying a current of I naught. Now through this I naught current is uniform current is flowing throughout that. Now from the top angle I consider a small loop which is inside. So this is the small loop which we consider from the inside. Now which is inside it, here we need to find the magnitude of the magnetic field. So in this present case, yeah, now in this case the small r is less than a. How we proceed? Let me take the formula. Closed integral of b bar dot dl bar equal to mu naught times I, current enclosed. So first I need to find these things. Here mu naught is constant and b bar I need to find. So two other quantities we need to figure it out. So the one is how much current is enclosing. So that is the first quantity I am going to find right now. And the second is what is the closed integral of B bar dot dl or closed integral of dl bar. So here Ampere loop is a circle of radius small r. So in this case we will get that closed integral dl bar equal to 2 pi r itself. Now let's bother about how much current is enclosing. Current enclosed. So this is very important. See, I naught current is passing throughout the conducting wire, but I need only the current where through the Amperian loop is passing. It means I want only the current which is passing through this my Amperian loop. I need not want outside the Amperian loop. We do not require that. So that's what the meaning of current enclosed. If you're calculating current which is not in the Amperian loop, then this law is failed. So that's why I'm giving a very careful caution whenever we try to use Ampere's law. First bother about the how much current is flowing through the Amperian loop. That's what we need to find. Now if you think just like logically to find current enclosed, so if A is the radius of wire and I naught is the amount of current is flowing, so what is the circumference? 2 pi a. Through the 2 pi a, I naught current is flowing. So if the total area 2 pi a, sorry, it's here supposed to consider area, not circumference. So through a of radius I naught, so its area goes to pi a square, area of the conducting wire. Now how much is the amount of current is flowing? In this case I will take this as I, just I you can take it. How much current is flowing? Through area of pi r square. It's just like chocolate problem. Suppose you are getting, for 2 rupees you are getting 8 chocolate. So for 1 rupee, how many chocolates you will get? Just like you will do the cross multiplication. Similarly, at here, through radius a, then the area of the conducting wire pi a square, through pi a square I naught amount of current is flowing, but I don't want the entire area. We want the point where we consider at a radius of r. Since it's also a circle, so circle area pi r square. So through my Amperian loop pi r square, what is the amount of current is flowing? Now here what I need to find. I hope you got it. One more time let me say. So because this is a very crucial point. Through whole area of conducting wire, that is pi a square, I naught is the amount of current which is flowing. But in this case we consider the radius which is inside the conducting wire. So through that particular area, how much amount of current is flowing? That is the meaning of current enclosed. Now to find the I, current enclosed, just do the cross multiplication. So if you can do the cross multiplication to get it I, so how much I can get? I equal to I naught times pi r square upon pi a square. Now pi is common term at here, so we can cut that. So I equal to I naught of r square upon a square. So this is the current enclosed. So this is the amount of current which is flowing through the Amperian loop, what we consider inside the current carrying conducting wire. Yeah, this value is less than that of the total current. Now here I got current enclosed value. Current enclosed equal to I naught of r square upon a square. Now we got what we required. Just plug in the given formula. So the Ampere formula says that Ampere's laws, the closed integral b bar dot dl bar equal to mu naught times current I enclosed. Now b bar we need to find. So here also I am going to find only magnitude, not the direction. So I drop here the bar vector notation. Closed integral dl bar equal to mu naught I. So b times here the closed integral dl. So this is the circumference of the Amperian loop. So we will divide the Amperian loop into small element length dl. Suppose if I divide, this is the small elemental length dl in the Amperian loop. So if I do the integration to all the elemental lengths, so how much value I get it? So we will get that the circumference of that, the closed integral dl bar equal to 2 pi r. So here r is the radius of the Amperian loop what we considered. So here I got that 2 pi r times mu naught. So here current enclosed, yeah, it's I only. Now what is the I value? I value here equal to I naught of r square upon a square. Now let's simplify it here. B equal to mu naught I naught r square upon 2 pi r times a square. Yeah, here r is cancelling but not the total. So b equal to mu naught I naught r upon 2 pi a square. See, all the quantities are the known terms. Here a equal to radius of the entire loop, radius of the conducting wire, and r is the point where we are trying to find the magnetic field, and mu naught I naught is the current, is both are constant, and 2 pi is also constant. If you can see this carefully, so here the magnetic field is directly proportional to r, the point where we consider in the conducting wire. So if this is conducting wire, yeah, from the center, now we consider the conducting wire which is up to at here. Now the magnetic field in this region which is inside, we are finding case which r is less than a. Now in this case the magnitude of magnetic field is directly proportional to radius. Suppose if we draw a graph, the graph between the distance means magnetic field b versus r. So this is at center, at point O, center. From center to till the edge, the B is directly proportional to R. The magnetic field at the center of the conducting wire is equal to 0. So from the center to till the edge, so its value is 0. Sorry, it is increasing proportionally. So this is at the edge. means at radius of A up to A. Since from the center to up to the edge, up to the radius, the magnetic field is directly proportional to the radius. And after that, from the radius to away, what happens? The magnetic field is inversely proportional to R. So that we got it in from the first case. So from the first case, from it here I got it that the magnetic field is inversely proportional to R. So at here we got the magnetic field is inversely proportional to R. So there we found that magnetic field which is far away from that. So if you represent that in the graph, so how we draw that? So B is inversely proportional to R. So this is some inversely proportional to graph. So it will fall just like 1 over R case. So this is B is inversely proportional to R. So from the center to till the edge, till the surface, so the magnetic field is directly proportional to R, but from the edge to outside, so the magnetic field is inversely proportional to R. So this is how the magnitude of the magnetic field is changes. But at the center, exactly at the center, or on the axis of the current carrying conducting wire, the magnetic field equal to 0. So this is also says about Bio-Savart's law also says about the same point. So this is how we will apply the Amperian loop for a given conducting wire and the Ampere's law to calculate the magnitude of the magnetic field very easily.